3.3 notes?
Yes, teacher.
Okay, so that means I can start lah. Okay, now I already live. So everybody, let's see. Let's start the lesson. Any question you can ask, you can stop me. So we start now. Okay, the others, Yong-en, okay?
Teacher, okay.
Mana Yong-en? Okay,
Teacher,
okay,
okay.
now we come start. Okay, okay, the others, start. Okay, let's see the 3.3. It's an electromagnetic induction. Before that, we learned about 3.2. Remember, there's a Fleming left-hand rule. Okay, I recall back the 3.2. Fleming left-hand rule, that means we're using the left hand. The situation for the Fleming left hand is they provide the current. They also provide the magnet. Then you need to find the direction. That one is Fleming left-hand rule. Example is a AC motor and DC motor. Cool? That one, the situation is they provide the battery. Then the motor how to rotate, then you're using your Fleming left hand to find the direction. Okay, now we go to 3.3 is electromagnetic induction means now don't have any battery. Okay, don't have any battery mean you need to do some rotation. Okay, example, you do some rotation. Okay, you do some rotation, that means you do some movement. The movement must be between the magnetic field and also the current. Then after that, they no current. The magnetic field and also the motion must be 90 degrees. After that, they produce a current. This one is an electromagnetic induction. Means you need to using the motion to provide the current. So now is no battery provided. I mean the whole situation, we cannot see got battery, we cannot see got power supply. You can see just a galvanometer. Why we put galvanometer? Because galvanometer can prove is it got current or no current. Okay, let me start the electromagnetic induction. Okay, let's see the first part. First part, they show about the definition. Okay, there's a production of the induced current. Okay, induced current. Okay, now we're going to see the induced current means the current that come out. We cannot say normal current. This one, induced current, the meaning is I generate to come up. So we call it induced current. Okay, after that they say without using the power supply. Without using power supply, but using the relative motion. Relative motion means you're using the movement, okay, between the conductor or you say magnet. So this one is a induced current, how to produce. Okay, what phenomena we using? The phenomena is this one topic, electromagnetic induction. Okay, so this one is a definition. Okay, then we continue go to following. Okay, let's see, we got two situations. Okay, wait, I go to add somebody first. Okay, let's see the two situations. Let's see the first one. Okay, relative motion of the conductor across a magnetic field can be produced by, okay, let's see first situation. Okay, this one is the first situation. Okay, now it's a solenoid. Then this one we call it conductor lah. Now the conductor is never moved. Conductor is stationary. Okay, coiled by the wire. Okay, now your magnet is movement. Okay, now magnet, they got magnetic field. Okay, surrounded, we got magnetic field. So that means when I move the magnet in, that means I cut the flux. Or you say you cut the magnetic field. When you cut the magnetic field means this one galvanometer later, they will deflected. Okay, deflected left or right later, we using the Fleming, we go refine it. So important now, we need to know is it got current or not. When you cut the flux, they will produce a current. So that means now the situation is one stationary, one moving. Okay, they will produce the induced current. Okay, then we go to second situation. Okay, the second situation is the magnet now is stationary. Magnet stationary, then this one is a conductor wire. Now the conductor wire, you move up and move down, move up and move down. So that means you cut the magnetic field. Okay, when you cut the magnetic field, okay, galvanometer also deflected. So this one deflected means they produce a induced current. So we got two situations here can produce an induced current. Either your magnet go in the conductor, either your conductor cut the magnetic flux. Okay, important it cut the magnetic flux. Either one to move. Okay, if both to move also can. Example, the first situation. Okay, you must move in opposite direction. Cannot move same direction. Okay, let's see the first one. Then this one, solenoid, you move to right. Okay, then the magnet you move to left also can. Like this, you also cut the flux. Okay, so we continue with the explanation. Okay, they say the first one, moving the magnet in a stationary conductor. Okay, B is the conductor moving in the stationary magnet. Okay, now we're going to see the situation C. Okay, C is moving a magnet and conductor in opposite direction. This one is what? Okay, this one no. It's just another example. When the first one, moving the magnet and conductor in opposite direction. So magnet and also the conductor opposite direction also can. Okay, last one is moving the magnet and conductor in same direction. Okay, same direction, but the speed must be different. Speed different means either one must be slow, either one must be fast. So you important make the magnet can go into the solenoid. Okay, they want call different speed. Maybe your magnet very fast, then your solenoid becomes slow. So the magnet still can go in the solenoid, that means you still can cut. So A until D is the situation to produce the induced current. Okay, then we go to following. Okay, let's see this one diagram. Okay, we got P. Okay, we got Q. Okay, first one, the P, they got battery. Okay, so the Q is don't have any battery. So important here, I'm going to show about the Q lah. How the Q can get it, the induced current, then the galvanometer will deflect it. So the first one, they say you close the opening for the switch S. Okay, you close already. Now you adjust the rheostat. Okay, adjust the rheostat, that means the current you are control. Okay, now flowing the coil P with the current and moving the coil P near to the Q. Move this one near to the Q. Then after that, replace the battery with AC power supply and keep closing the S. Then we see what happened. Okay, then later we're going to see the result. This one is what they want you to do. Okay, then we see the last one situation. Okay, last one is two magnet. Okay, they got two magnet bar. Okay, now they got oscillating the pendulum bob. Okay, pendulum bob at the middle. Okay, when they just oscillate means they cut the flux, is it? Here center got flux. When the metal ball, the bob, they just cut the flux. Okay, then this part they join with the galvanometer. Then the galvanometer also will be deflected. Okay, so this one means now the ball is cutting the flux. After that, they generate the induced current. Although not exactly 90 degrees, but still got a little bit current unless you are parallel. Okay, parallel is nothing happened. So from here, when the relative motion between the conductor or the magnet happen, the conductor cut the cross about the magnetic field. When they cut the magnetic field, so after that, they will change of the magnetic flux. Either you cut the field, either you change about the magnetic flux, induced current also will happen. Okay, now we're going to see the first diagram. Okay, if I put the magnet in, so you find it like this. Magnet got flux. When I just go in, the flux is cutting by the solenoid. Then this one will be deflected. The second one is, okay, the magnet between, they got flux. Then you move the conductor up and down. Then you also cutting the flux. Then galvanometer also will be deflected. Okay, third one. Third one, just now they say closer, is it? You bring this one solenoid closer to the another solenoid. So you find it, they will link to the another side. They will link to the another side. After that, they will automatically generate the induced current to the second circuit. Then the galvanometer will be deflected. The last one same lah, just like what I told you just now. Okay, one still want to go in. Okay, let's see the last one. Last one is a ping pong ball. Oh, not ping pong ball, that's a bob. Ping pong ball cannot. Though this one is a bob. Okay, so you find it, this one got magnetic flux. So when I just swing the bob, so you find it, they cut the flux. So galvanometer also will be deflected. So this one is an introduction. Introduction to show how come the induced current can produce. Okay, induced current want to produce, first one, you must have the motion. Okay, number two, you must have the magnetic field. Okay, magnetic field. Then after that, these two must be cut. Okay, cut 90 degrees is a perfect lah. Okay, if you cut the 90 degrees, that means you can produce a full of the induced current. Okay, so we're just talking three things only: motion, magnetic field, and also induced current. Okay, so now let I show you some diagram. Okay, this one is the first one. Okay, just like the normal magnet, go in the solenoid. Hello, Justin, can see the diagram or not?
Can, teacher.
Can, okay. Now this one is a magnet. They go in the solenoid. So solenoid join with the galvanometer. When you just go in, galvanometer will be deflected. So this one is the first one. Okay, then I go to the second one. Okay, second one just like this one. Okay, just now I told you the magnet is a fix. So I'm using the conductor wire. I go to move. Okay, move up and move down. I cut the flux. So galvanometer also will be deflected. So from here, they explain for you, deflection of the pointer of the galvanometer means there's a current flow. Bigger deflection means bigger of the induced current produced. So this one is what I want to show you. Okay, next, we're going to see the next one. Next one should be this part. Okay, this one is another thing. Just now I show you. One is with current, you got power supply, another don't have. So when I bring the closer, you see the flux, they will attract to the another solenoid. So this one galvanometer also will be deflected, but you need to put closer lah. When you put closer, that means you got the flux, the motion will go another side. So you find it, they also will be attached. The flux go another side, then this part will be deflected. Okay, then, okay, no more. So we need to go the following lah. When you see the following, how come this situation will happen? Okay, so we go down. Let's see the first one I want to introduce. Okay, I want to introduce the first one. There's a Lenz Law. Okay, let's see Lenz Law, what they're talking about. Okay, you want to determine the direction of the induced current. Okay, so we're using the first one, Lenz Law. Okay, let's see the Lenz Law, what they're talking about. Lenz Law, they state that, okay, the direction of the induced current always flow. Okay, induced current always flow, okay, in such as a direction, so to oppose the chain which causing it. Okay, anybody here can understand this sentence? Okay, anybody here give me the opinion what you means about in such as a direction, so to oppose the chain which is causing it? Okay, anybody want to explain? Open your mind, on your mind, just tell me what's the meaning of this sentence. Not understand. Okay, so we just forget about the words. Okay, we're using the concept to let you to understand. Okay, the meaning is you want to produce the induced current, they say by using the Lenz law. Okay, this sentence, the meaning is the direction. Okay, the direction of the magnet you want to go in always oppose the chain. Oppose the chain means here they always got opposite thing, don't let you to go in. If you want to go in, okay, here they say oppose the chain. Oppose the chain means they want to reject you to come in. So this one is, I don't care you want to come in or go out. If you want to go out, that means here got one of the oppose the force. they don't let you to come out. So this one we call it oppose the change. Because of this one oppose the change, finally they produce an induced current. Okay, so from here, example, for this one situation, there's a go in. Okay, we're going to see what happened. Okay, now the magnet, they want to go in. Okay, after that, I say oppose the change, follow the Lenz law. So that means here is a north. Okay, if I say I don't let you to go in, you tell me this one should be, okay, wait, find my pen first. Okay, this one is a north. So I say I don't let you to go in. You tell me this one should be north or south. Don't let you to go in. Sure, here is a north, is it? Don't let you to go in. If I put south means you can go in already. So we follow the Lenz law. Here, automatic, they will become north. Okay, because they oppose the change. When they oppose the change, okay, you cannot go in. I got force, don't let you to go in. So this one is a repulsive force. But finally, you still can go in because you push what, is it? So from here, I know this one is a north pole already. Okay, because you want to go in, then the repulsive force. So from here, if I know this one is a north pole, sure, this one becomes the south pole. So we're using my right hand grip rule. Remember the right hand grip rule? Okay. Excuse me, you see my cam, is it? Can see my cam or not?
At the corner, teacher.
Okay, so I show my hand. Okay, so from here, right hand grip rule. So you take out your right hand. Okay, remember the thumb is represent north. Okay, right hand is represent north. So I point to right hand side. Okay, when I point to right hand side, can you see your finger, your forefinger? Forefinger now is a magnetic, the come down, is it? Come down is represent the current. Okay, come down is represent the current. So now thumb is go to right, then the current is grip in. Okay, grip to come down. So it grip to come down now, you're going to see the follow the diagram. Come down means the direction all become like this. Okay, if all become like this, okay, means until this part, then this one will be up. So how the galvanometer go to deflected? Okay, before that, the galvanometer always 0 is at the center. Okay, now your current is moved like go to right hand side. So that means later your galvanometer will deflected, go to right hand side. Okay, this one is Lenz law. Lenz law never show anything. They just say the situation is magnet want to go in solenoid. Then after that, they produce the oppose the chain forces. Okay, because of this one oppose the chain forces, then produce the induced current. Okay, so they never say how to make it become strong, how the magnet can go in faster. They never say like this. They just say for this one situation only, how to produce induced current by oppose the change which is causing it. Okay, this one is a magnet in. Then we go to second page. There's a magnet want to come out. Okay, second page. For explanation for just now. Okay, let's see here. When the magnet is moved towards, they want to go in. Okay, now, after that, there is a force repellent assist. That means you got repulsive force between the solenoid and the magnet. Why got this one? Because we follow the Lenz law. Okay, now the end of the induced. Okay, end is the induced to become the north pole because you want to go in. After that, they got opposite force, you become north pole, and the direction of the current now is from the A go to the B. For A or B or not. Okay, you just stand there. Another side, the galvanometer. Okay, example, right? This one, this one is A and B. Follow just now diagram. Let's go to A to B. Okay, galvanometer A to B. This one is a just now diagram. Okay, then we go to this diagram. This one is terbalik. Can you see now the magnet want to push away from the solenoid? Okay, now the magnet, they want to push away from the solenoid. I want you to see the last part. The last part, don't see the in front, see the back one. Okay, this one N is it? They want to go out. Okay, now we follow the Lenz law. Here must be don't let you to go out. Just now is you come in, I don't let you to come in. Now you want to go out, I don't want you to go out. So from here must be southpaw. Southpaw means you want to attract the north to come back. So this one we call it, they got attraction force. Okay, because this part is a southpaw, so understood this one is a north pole lah. So when you come out, now you need to using your right hand grip again. Okay, right hand grip means now the north is go to left hand side. So you take out your forefinger, now you grip. So example, I go grip my pen, so I grip. Okay, you see my forefinger is go down. So that means when I draw, follow this part, this one is an arrow. Okay, so this one is an arrow until they go behind, then this one come down. Okay, you follow the external galvanometer. Now there's a from B go to A. The deflection is from the B go to A. Okay, now we go to explain. When the magnet is moved away from the solenoid, they got force. This one we call it attraction force, exists between the solenoid and the magnet. Okay, now the end of the P. Normally end of the P, they're talking about this one lah. End of the P will become the south pole, and the direction of the current now B to A. Okay, the work done is convert become electrical energy. Can you see? Normally we get electrical energy, then do the work, is it? Now for electromagnetic induction, we terbalik, we using the motion, we using the kinetic energy to convert become electrical energy. So this one we call it induced current. Okay, not simply called induced current. You on the electrical, after that your bulb on, that one not induced current, that one is current. Okay, this one because of the, you're using the motion to convert electrical energy, then you create the current, we call it induced current. Okay, any question you want to ask?
Teacher, no.
No, nothing to ask. Okay, if nothing to ask, then I see any diagram to show you. Okay, let's see here. Okay, this one is one of the diagram for the Lenz Law. Okay, you can see the same, the thing must be the same lah, just I show you. Okay, the direction of the induced EMF, you can say induced EMF, you can say the induced current. EMF is a voltage, is it? So we put it's an induced, you cannot say EMF only, we say induced. Okay, such there's a magnetic effect always oppose the change. So this one is a Lenz law. So from here you see the first one. First one they show the magnet they want to go in, is it? This one N, then they got repulsion force, then produce an N. So when you want to go in, then this one become N. Okay, using your right hand grip, then you find it, all the current is up. Yeah, Jane become red. Okay, all the current is up. Okay, all the current is up, and they go up, then this one is, then this one down. So you find it, your galvanometer will deflected to the left hand side, right hand side. Okay, this one another side. You want to quit, you want to away. When this one is an N, this one must become the sub. Okay, because of this one solenoid cannot clear, cannot see clear. So they show like this, then we just follow lah. And this one is come down, this one is go up. Okay, just this one is a Lenz law, what they're talking about that. They're just talking magnet go in solenoid only, no others. Okay, then we go to see another diagram. Okay, this one also is one of the thing, same like what I told you just now. Yeah, I put at the center. And you can see about this one. Also same lah. You want to go in, then this one is a southpaw. Here automatic they will generate become south. Okay, now you want to away, you are southpaw to away. Here will continue generate become the north. Then after that you need to using your right hand grip, then you find the direction of the current. Okay, the current produced we still call it induced current. Okay, then we'll see some more. Okay, this one is a one example question. Okay, this one very clear. Okay, first one I show, let's see the first diagram. Okay, north, they want to go in. Okay, understood here become north lah. Okay, understood the bottom here become north lah because you want to go in. Okay, this one become north. Now you take your hand, right hand grip, then you grip. Okay, when you grip, okay, now the direction is come down. Okay, now the direction is come down. Okay, go here. Okay, this one galvanometer. If I say AB, so that means now your current is point from A to B. Okay, magnetic field lines are being cut. Okay, we see the second one, B. Now is I go in, I stationary, I never move. Just go in, then stationary already. Okay, when you go in, okay, galvanometer got deflected, like this one first situation. Now continue. When I just go in already, then I stop. Okay, if I stop at the middle, nothing happened. Now you find it, the galvanometer will go back. Go back to the zero. Go back to the zero means no deflection already. The galvanometer means now is no induced current. Okay, induced current must keep moving, you know. If you're stationary, that means nothing happened. They will go back to the zero. Okay, now from the C, now I want to pull out already. Okay, when I pull out, this one want to away, this one must become the south. Okay, if this one becomes south, this one becomes north lah. So you point again your finger, north now is left hand side. So now the current is up. Okay, now the current is up. So that means this one is up, this one is down. Okay, A, B again. Now your galvanometer deflected, go to the A. Okay, from the B, from the zero, go to the A. Just now is from the zero, go to the B. So current is induced in opposite direction. Bar magnet move out from the coil. Okay, now moving the coil towards to the stationary magnet. Okay, now stationary magnet. Magnet never move. I make the coil closer. When I make the coil closer, also same. You want to closer, mean this part is a north. This part is a north. Okay, here you want to closer, is it? Closer mean you want to let the magnet to go in, is it? Here also got opposite force, repulsive, don't let you to go in. So now this one is a north again. Pour your finger. North go to right, finger is go to your side. So that means deflected again from the A, from the center, go to the B. Either you move magnet, either you move the coil, also can. Okay, remember, just want to go in, don't let it to go in. If you want to come out, solenoid, don't let you to come out. So this one is a Lenz Law concept. Okay. So from here, so no question, Anybody want to ask? Okay, nothing. I continue to open. Okay, now we need to go to the notes already. Okay, we need to introduce direction. Just now I told you how to find out direction, is it? Okay, let's see. Fleming. Okay, now it's a Fleming right hand rule. Right hand, prepare your right hand, no left hand already. Okay, now you're using the right hand. Okay, now you want to find the direction of the induced current from the dynamo. Dynamo means generator. Generator means we never using the power supply. We go to generate to come out the electricity. Okay, now first finger, still magnetic field. Okay, this part should be the north. This one is a south. Then you point. Okay, so like this lah. If the north to south, that means you point far away from you. Okay, the second finger still current. Second finger still current. Okay, now the first finger still motion. Okay, we can say about the force lah. Okay, you can say about the motion. Where's the direction? Okay, now the problem is, question will provide motion. Question will provide magnetic field. They want you to find direction of the current. Okay, now we're going to show this part. Okay, let's see this one diagram. Okay, this one diagram is, we do know the current. Okay, assume we do know the current. They show you the P to Q, is it? Assume we do know. Okay, now we check. S north. Okay, now I want you to take out your right hand, point north to south. Okay, the situation might be like this. You point to your left hand side. Okay, now can you see the wire is go downwards? Can you see the big arrow go down, is it? So I want you to take out your thumb. Thumb is a motion, Take out your thumb. Show the thumb go down. So I turn, I turn, go down. Okay, can you see? My thumb is go downwards already. My magnet never change. My magnet every time point to the left hand side. Okay, now I take out my second finger. Can you see my second finger is far away from me? Okay, far away from me means now the current is from P go to Q. Okay, P go to Q. Okay, if I terbalik, now I want to say the conductor move upwards. So I point again, north to south. Okay, then after that, take out the second finger, conductor, not conductor, this take out the force first, the motion. Okay, now the motion is the conductor wire move up. So I point my my thumb go upwards. Okay, now you take out your second finger. Your second finger now is point yourself. Point yourself means the current is come from Q to P. Okay, so from this one situation, the conductor wire go downward, so the current is from P go to the Q. Okay, P go to the Q. Okay, so that means we're using a Fleming right hand to find out the current, where they go. Okay, so now we want to show you the diagram for the Fleming. Okay, this one is a Fleming right hand rule. Okay, magnetic field is the first finger. Okay, remember this one north, this one is a south. Okay, this one is a current. Okay, this one is current like this, mean go downwards lah. Okay, we do know the induced current. Induced current is a final, you need to find it. Okay, thumb is the motion of the conductor wire. Okay, if the conductor wire go up, then you move up. So your thumb will show upwards. Then after that, you will see the induced current where they go. The induced current is either come to you or either far away from you. Okay, so from here we go to explain producing of the induced current when there is a change or cutting the magnetic flux by the conductor. Can you see the thumb and the magnet now is a 90 degrees. 90 degrees, I mean they show like this. 90 degrees. If you know 90 degrees, you are parallel, actually nothing happened. So must be 90 degrees. After that, your second finger is go downwards. Okay? So depends for yours. You want to point yourself also can. You want to go downwards. So either up, either down. So this one is an induced current. Later we're going to see some explanation for some example question. The conductor wire go down. Okay, point for me, conductor wire now is go down. I want to know the current is come to you or far away from you. Okay, you point for me, okay? So anybody please answer. I want to know the current is dot, the current is dot, or the current is cross.
Dot.
Dot, okay. You see, north to south. Okay, now I say the wire go down, is it conductor wire go down? Then I need to point downwards. Point downwards, then I take out the second finger point myself, is it? Point myself means the current is come to you. Come to you, the answer should be dot. Okay, dot is correct lah. So that means if the wire now go upwards, wire go upwards. Okay, wire go upward means the second finger far away from you. That one is a cross. Okay, so just the same thing. Same like what we learned for Fleming left hand. Just the ballet want to find the physical quantity now. Okay, so please ask any question. Okay, this one is another diagram. Okay, make it bigger. Okay, let's see this part. Okay, this one is north to south. This one more easy to show lah, because the hand still easy to be show it. Okay, let's see here. This one is a north, this one is a south. Okay, now the conductor wire, how to move? The conductor wire is move up. Okay, movement is a up. So the first part, we point the north to south. You see, the hand show you already, north to south. Okay, if the direction movement of the conductor is up, then I show the motion. The thumb is up. Okay, now you take out your second finger. Your second finger now point yourself, is it? Point yourself means the current for this one conductor. Okay, this one conductor example lah. They join with the galvanometer lah. They join with the galvanometer. Oh, you see my drawing. Okay, this one is 0. Okay, like this. Okay, they join with the galvanometer. Okay, now this one current is come to you, is it? Come to you means go here lah. Go here, then go back lah. So that means this one situation, I cannot, if I put like this, I cannot see clear. So if the 0 is another direction, like this, nothing happened. Okay, if I put the 0 is here. Okay, drawing. Okay, if I put the 0, where's my pen? Okay, I put the 0 here. Okay, so now if the current go, okay, where they pass? They will deflected go to the this situation. Where they follow ma? Go to here already and go back. Okay, understand? So if I terbalik, now the situation is I move the conductor down. What happened? So you point again now, move your conductor down, take out your thumb now will turn downwards. Now second finger is far away from you. Far away from you means the arrow far away from you lah. If far away from you, now the current like this. Okay, go back. Until here, go back. Okay, go back. Okay, so from here, this one the deflector, the deflector go to this side. Okay, anybody want to ask about the question?
No, teacher.
Okay, so I just going to see got any diagram or not. Okay, later I want to show is this part. Okay, after you know the Fleming, then later we need to see the, also same. They also like the, you learn about 3.2, the motor to turn, is it? Okay, this one also is a motor. The problem is, we never say about motor. Motor is using the current. This one we call it as a dynamo, or you call it as a generator. Okay, this one situation, you see they're using voltmeter. That means they don't have any battery here. The voltmeter, if got current, that means later they will deflect it. Okay, so from here, voltmeter cannot start from center lah. The 0 is at the bottom one. Okay, so from here we do know the current. Okay, we do know the current, actually no current. So now the coin here. So I go to label the coin first. Okay, I label this part is a A, then this one is a B, then this one C, then this one is a D. Okay, so how to rotate, it depends for you. Normally the rotation might be same direction lah. Okay, one rotation of clockwise, every time is a clockwise. If you left and right, that means later nothing happened. Okay, so from here, first one you put the north and south. Okay, then after that you go to rotate. Okay, rotate now is a clockwise. So this one, the force is go up. Later the force is come down. Okay, the rotation like this. So now I want to know the current, how to flow. The current flow ABCD or DCBA. So for first round, we go and find the easier one. Either green color, either yellow color, up to you. So now I point the north south first. I point the north to south. Okay, easier one must be up lah, is it? So I take about green color. That's A to B. Okay, so now F is up, is it? The force is up, so I take out my first finger. Okay, first finger is up. Then I show my second finger. The second finger is far away from you. Okay, agree, far away from you. So that means now the green color part is far away from you. That means A go to B. So understood this one is go downward, then the C to D. Now the current, how to flow to the internal. Internal is A, B, C, D. Okay, how about the external? Okay, if I label this one P, this one Q. The external is from the P, then go to Q. P, go to Q. So that means your voltmeter later will deflect it. Okay, deflected means sure up lah, deflected. Okay, deflected, that means they got current pass through. The whole circuit got run. Okay, so terbalik, if I terbalik the situation, when you turn terbalik already, your voltmeter also later will show the deflection. When they just show deflection, I know got current to go through. Okay, because now they never show galvanometer. If galvanometer means you go left and go right, the voltmeter is always go to right. So when it just got refracted, then we know this situation, they got current. Okay, so after you know the Fleming right hand, then this part. This part is just now what I show you lah for the generator. Okay, remember the center part, we call it as a commutator. Okay, commutator, this part, commutator. Okay, this one still the carbon brush. Okay, now we join with galvanometer, no battery. Okay, so from here, north to south. Now I got label Z, X, Y, W, Z. Okay, now rotation, I tell you already, the rotation is anti-clockwise. Means this situation is up, the force push up. This situation is the force go downwards. So you take out your right hand again, north to south. Okay, we do the easy one. Normally the thumb will show up, is it? So we take the side XY. Okay, we see the XY. So when you north to south, then XY, the force is go up, then I show up. So where is the second finger? Second finger, point yourself. Point yourself means the current how to flow? X to Y. Okay, if X to Y means come out here, come out, then this part must go in, then go in this part. So external, the current how to flow? X, Y, Z, W. Or you can say Z, W, X, Y. Okay, it's the same thing, but we start here lah, Z first, then go in. External how to flow? If I label this one P, this one Q, P to Q. From the P, go in, then go out, Q. So galvanometer, how to deflect it? Okay, galvanometer with deflector go here. Okay, because from the here, they will go in. Okay, so this one is how the rotation of the generator. So from here, they say from when the coil WXYZ is rotate, then it's the anti-clockwise direction of the induced current is from the X to the Y. Where's the X? Where's the Y? X to the Y. Here lah. The current in the coil, there's an X to the Y. Then after that, this one is Z to the W. Okay, the question must tell you how to rotate. Must tell you how to rotate. Then after that, you find the galvanometer how to deflect, or you find the current how to flow. Just like this only. Okay, so this one is chapter 3 from 5. So from 5, we just got 3 bulb got experiment. Chapter 4 and 5 actually is no experiment. So this one is the last experiment for the from 5. So from here, I told already SPM paper 3. They got 2 of the experiment. You need to choose one. Is it? One is a form 4. Another one is a form 5. So form 5, we just until chapter 3. Okay. Chapter 1 wave. Chapter 2 electricity. Then chapter 3 for this one is the last experiment. So we're going to see the experiment about the induced current. Okay, before go to experiment, they must got the factor. Okay, let's see the factor from the Faraday Law. Okay, let's see Faraday Law. Okay, to determine the magnitude of the induced current, they want to find the value of the induced current, okay, by using the Faraday Law. Okay, what the Faraday Law they're talking about? The magnitude of the induced current directly proportional. You want to produce more induced current, okay, they must directly proportional with the rate of change of the flux. Okay, rate, remember, time taken to change the flux. If you 1 second you change more flux, that means you produce more induced current. Okay, or you can say rate which of conductor cut through the magnetic flux. Either you change the flux, either you're using conductor go to cut the flux, that one also will produce more induced current if faster. So that means this one is a Faraday Law. Okay, directly proportional. So we're going to see the induced current, how to increase. First one, you say you increase the number of turns. Remember, if this one is a solenoid, okay, if I make more turn, then your magnet want to go in. That means you cut the flux is increased because they got more turns already. Second one, increase the strength of the magnet. Use a strong magnet. Strong magnet means the magnetic field more. When you go in, also cut more flux. Okay, last one. Moving the magnet or you moving the solenoid faster. Okay, make sure opposite direction. Okay, if you want faster, after that you want to produce more cutting, sure it's opposite direction. Then you can cut more faster, more flux. So this one is a 3 situation how to make the induced current become strong. Okay, so I want to make the differences about Faraday Law and Lenz Law. Lenz Law never talking how to increase the induced current. Lenz Law just talking how the induced current produced. Because of the solenoid and magnet, when they move in opposite, change the direction. That one is Lenz Law. Faraday Law is talking about the factor, how to make the induced current become stronger. That one is a Faraday Law. Okay, so because they got so many factors to make the induced current become stronger, so they got experiment. Okay, let's see the first one, relationship between the magnitude of the induced current and also the speed of the relative motion. That means you move faster, induced current must be more. Okay, let's see this one experiment. You tell me which one should be manipulate variable.
Induce.
Induce actually.
Teacher, here got right,
Then you follow
speed,
here lah. That's why wrong lah. That's why I told you lah. You follow here, then wrong lah. Okay, help me to switch. Wrong already, this one. We cannot control the induced current. We just can control our speed. Okay, now I will ask, if you say speed become manipulate variable, how to control speed? Don't tell me using the ticker tape lah, using the trolley lah. How to control the speed? Anybody can tell? How to control the speed lah? You can count the speed lah. 1 ms maybe 1, 2 ms maybe 1. How to count? Kaje. Kaje. See, Kaje go already.
Yes, teacher.
Okay, you tell me how to control the speed.
Control fast and slow only.
How to fast and slow? How fast? You tell me how to count to fast. What means of fast? Physical quantity we need to measure.
Don't know.
Don't know. We learn here or not? We learn not here. Okay, let's see diagram. Can you see the magnet? The magnet later will drop. Okay? So I explained again. I give you hints already. The magnet later will drop in the solenoid. That means they drop in the solenoid means they cut the flux. Okay. Anybody can tell me how to control speed? We're using the different height. Okay, we're using the different height. That means you can control the speed. If you put higher, mean the speed you drop become fast. So that means now the manipulate variable, you help me to change. This one become MV. So I cut here. I show the diagram. I show the arrow already. So this one is a RV. This one is a MV. Okay, we control is the speed of the relative motion. Okay, you don't want to write the speed, you can write the height of the magnet. Also can. Okay, but the responding variable sure is an induced current. Okay, now because your MV is a height, is a speed, so the number of turns of the solenoid must be constant. Yeah, this one become constant number. Okay, now we list the apparatus. Okay, we got galvanometer, we got solenoid bar, we got solenoid, after that we got bar magnet, then you must have the meter rule. Why must have the meter rule? You measure the height. Okay, you measure the height of the magnet. Okay, the diagram like this only. Okay, ruler you don't want to draw is up to you. So important you got magnet. Then after that you got solenoid bar. Then after that join with the galvanometer. Then after that this one will drop. Okay, when you drop, galvanometer will be deflected. Okay, deflected. Okay, so from it, actually, this one experiment cannot to show as a practical because the galvanometer later deflect is very fast one. You cannot take one. Okay, you just want to see is the anchor bigger or anchor smaller like this only. Okay, if you put the magnet higher, then when they drop, the galvanometer will show the anchor bigger a little bit. So that one means cutting flux is more. Okay, so this one is one of the experiment. Okay, now we go to the page number 3. Okay, we see how to write this one report. Okay, now procedure. Okay, first one, the height of the magnet above the solenoid, the measure meter rule, 50 cm. You put 50 cm means the highest one. Okay, after that, they say the magnet is dropped into the solenoid and the reading of the galvanometer is recorded. There's an X. Okay, we put X. Now experiment repeat. Okay, at least 4. Here they give you 5, you at least 4. So you need to mention. Now, just now is the maximum. Now you drop. Drop until, okay, 30. Then finish. So this one is a explanation for a procedure. Then you got MV already lah. MV is a 50 cm. So RV is a X, is it? You must say the magnet drop into the solenoid. Okay, after that, the reading from galvano. Then you record there's a X. So this one is a RV. Okay, this one is a repeat. Okay, repeat at least 4 times. Okay, then after that, there's a table. Then this one is a analyzing. Okay, analyzing, this one is a height. And this one is an induced current. Okay, so this one is a one experiment. So if I terbalik the experiment, just now is a height, is it? Now I say number of turn. Height, that means the speed become constant. How to make the speed become constant? I make the height become constant. I make sure there's always 50 cm. The magnet always 50 cm. After that, this one is a solenoid coil. Okay, join galvanometer. Okay, then after that, I drop. Okay, still the same thing. Just you say, okay, when starting, I'm using 10 turns. Then repeated using 15, 20, 25. Okay, continuous. So this one is what I want to tell you. There's another experiment. Okay, the first one is speed. You control the motion. Number 2, when you control the motion, then the constant variable must be the number of turn. If terbalik, number of turn become responding variable, then your location for the magnet must become constant variable. Okay, so this one is 2 experiment. Okay, third one. Now, speed constant, the height you constant. Number of turn I also constant. Now I say magnetic field become responding variable. How to make the magnetic field become stronger? Hello? Magnet. Now I want to adjust magnet. How to make the magnet become stronger? Now it's magnet. Experiment is the same. MV. Now I want to change become magnet. The MV control the magnet. Responding variable still induced current. Induced current. Okay, constant variable now you can say about number of turn. I want to constant already. Okay, you also can say about the height. Okay, now the manipulate variable I want to say about magnetic field. Okay, how to increase magnetic field? You tell me how to control. Then meter rule is here, magnet is here. You put in the solenoid, join with galvanometer. Okay, this one magnet. How to control the magnetic field become stronger?
Teacher can change size of magnet or not?
Can, using the bigger size law.
Can
Okay, but you using the bigger size, they're not constant, is it? How to bigger size? 2 cm, 3 cm, 5 cm. You never measure the magnet like this. Then we using 2 magnet join together, law. Understand? 1 magnet bar, then I use 2 magnet bar, then I stick together lah. Now you become the magnet becomes stronger already, become powerful. Then I stick 3 magnets together lah. Then I go to drop. So that means this one is how to control the magnetic field. First bar of magnet. When you repeat, 2 bar of magnet, 3 bar, 4, and 5. Then this one will make the magnet become stronger. Drop inside the solenoid. Make sure your solenoid is big enough lah. The hole, let the magnet can be go in. Okay, if your hole is small, how to go in? So that means the magnet bar, you can increase the bar of magnet. So this one is how to increase the magnetic field. So from here, got 3 experiments can come out. Either increase magnetic bar, either you go and increase the number of turns, either you go and increase your height. So this one is a last experiment for Form 5. Okay, any question you want to ask? Okay, the magnitude of the induced EMF, or you say induced current, that's a directly proportional to the rate of change of magnetic flux. Remember, magnetic flux rate to change experiences by the conductor. So Faraday, they're talking about you must change the flux in short time. Then after that, they can produce more of the induced current. So this one Faraday law. Then we're going to see another diagram. Okay, this one is the explanation, the Faraday law. Okay, they say the magnitude of the EMF in the wire increase when, okay, how to make the magnitude of the induced current increase? First, the wire move faster. Okay, 2, a stronger magnet used. Number 3, the length of the wire EMF is increased. Why the length increase? They become strong. Okay, the length of the wire you cut, the conductor you cut, make it longer. Longer means you cut more flux. Okay, you shorter, you cut a little bit flux. Make longer, they cut more flux. After that, they can increase the induced current. Okay, don't think about wire longer, resistance big, then the current how to big. No, that's not related. This one is the length of the wire to cut the magnetic flux. Okay, different things are. Okay, now the magnitude of the EMF in the coil increases when, okay, in the coil, now it's coil, the magnet go in, relative motion between the magnet and the coil increase. Means the magnet, you move in the coil faster. Number 2, number of the turn in the coil increase. Number 3, the cross-section area of the coil is increased. If your coil, the cross-section area become bigger, then you turn, the wire must be more. Because your area become bigger already. Wire turning become more, that means the magnet, when they go in, also will be more flux to cut. Okay, this one is a 2 situation. First, magnet never move, conductor move. Second situation is conductor never move, magnet go to move. So this one is a 2 situation, how to make the induced current become stronger. Actually, 2 also is a Faraday law. Okay, then we're going to find out some more of the diagram. Okay, no more already. So I want to show is a generator lah. Okay, later I will show this part. Okay, dynamo. So this one is a DC dynamo. How we go to see it, there's a DC or AC. Okay, DC and AC is external. You need to see is later, the external circuit, how to flow. If DC means every time in same direction. If go from the left, go to right, every time is from the left, go to right. Okay, we're going to check this part. This part never show about current, how to flow, but they give you the rotation. Okay, you see this side. So better I label A, B, C, and D. Okay, now B is up, C is down. So that's why the rotation is a clockwise. Rotation is in clockwise. Okay, now we need to show about direction of the current. Okay, north to south. Okay, north to south. Okay, we easier one. We show the part B. Can you see the part B? The rotation is up. So the thumb is up. So that means I take out my second finger. Second finger now is far away from you. Far away from you means A go to B. Okay, A go to B. Okay, if I check about the another side, D and C, DC, okay, D to C. Now can you see the force is go downwards? So I need to turn. I need to turn my hand, go downwards. Okay, you see the second finger, point yourself. Point yourself means C go to D. Okay, this one is A go to B. So that means outside how to flow. This one go in, this one come out. Okay, because I put the bulb, never mind lah, the bulb also cannot show you the direction, is it? I just want to see the bulb got light up or not. When the bulb light up means got induced current. Okay, so the current how to flow now from inside the internal, there's a from A, B, C to D. Okay, if I label PQ, external, okay, external how to flow from the P, go to the Q. Okay, so now from this one dynamo, later they turn about 360 degrees. I want to show every time the current for the external must P to Q. Although your turning coil later is terbalik, the outside the current always P to Q. If I say the outside always P to Q means they produce is a direct current. Okay, so now I want to go is the following. There's a 4-part turning. 4-part turning of the generator. Okay, now we go see the page. Okay, open the page again. There's a page number 3. Okay, so we continue for rotation. Now is a application for the electromagnetic induction. Current generator. Current generator function is converting mechanical energy to electrical energy. The mechanical energy now is a kinetic. They're using the rotation convert to electrical energy. Electrical energy is an induced current. Okay, now the current generator work based on, okay, if they ask what phenomena, you must refer to the topic's name, electromagnetic induction. Using what concept? We're using the Fleming left-hand rule to find out the induced current, how to rotate. Okay, how to produce, what the direction. Okay, now the first one, I will show you the DC generator. Okay, later is an AC generator, or also generator, no battery here. Okay, let's see the DC first. Okay, commutator, carbon brush. Okay, now we go and check the current how to flow first. ABCD or DCBA. Okay, now you point north to south. Okay, we see the easy part. This one force is go down. This one force is go up. So that's why there's an anti-clockwise. You see the part C and D. Yes, C and D. C and D, you point your thumb is go upwards because the force is go up. So the second finger is far away from you. Far away from you. So far away from me means I need to write D to C. So D to C. So this one is B to A lah. Then after that, when they come out, okay, then go here. Okay, so if I label this one is XY. So how the current flow in external? External is X go to Y. Okay, internal is A, B, C, D. The current flow in the coil is, sorry, not A, B, C, D, it's DCBA. You see, I do wrong already. Nobody answered me. Okay, all right, again. External. External, if you from here is okay. X, Y, still okay, external. X to Y. Okay, so from here, you outside my X to Y. Then inside is a DCBA, not A, B, C, D. Because I count from here. D to C, B to A. Okay, then X to Y. Okay, this one is how to flow. This one is a generator, the starting one. Okay, now I will need to go is every part to rotation. We're going to see the first part. Okay, first part, internal, I label A, B, C, D. Okay, external, can you see one part is a black color, one part is a white color? So later we will turn about 180, they will terbalik one. Okay, now we're going to see north to south direction like this. Okay, so now turning, can you see the turning? Turning is anti-clockwise, always anti-clockwise. So this one up, this one is down. Oh, sorry, terbalik. So this one is down, this one is up. Okay, now I need to know galvanometer go right or left. This one is right, this one is left. Okay, you show me. Left was a lot. Okay, tell me galvanometer how to rotate. Never rotate is a center, 0. Left or right?
Right.
Right. Okay, some more? Some more? The others?
Hả? Some more à? Oh.
Internal, you tell me internal now. Internal coil, how to move the current? ABCD or DCBA?
DCBA. 我也是不会，是吗？
Now we check. You say DCBA, is it? Okay. Okay, we check. This one outside you say R, is it? Right, is it? Okay, now we go and check. Okay, now point again, north to south. Okay, now I want to show is a part C. Can you see the part C? The arrow is up, so the arrow is up. So D to C lah, because the arrow is far away from you. I point the second finger far away from me. So I need to draw here, north to south, then DC, then BA. So DC, BA is correct. When it just come out, okay, here, then go back. So that means later the deflector of the galvanometer is deflect, go to the right hand. Okay. So Justin, you are correct. The rotation. Here the current, how to move also correct. Okay, this one is the first round. First round, okay, we know internal is DCBA, external is go to the right. Okay, now we go in second part. Okay, before go second part, we need to answer the question first, fill in the blank. If the question, this one fill in the blank, for the exam, no fill in the blank, you need to write all. Okay, coil AB move downward. You must say coil AB where to move first. The question show, the diagram show you. Coil AB go downwards, coil DC go upwards. So you mention how they rotate first. So the first one, AB downward, CD upwards. When the coil rotate, its side will cut across the magnetic field. Okay, you must say cut the magnetic field line, or you say they cut the flux. Then after that, induced current produced, is it? Now the induced current, they flow in the coil from, okay, now you need to say in the coil, how they flow the induced current. This time we prove already. There's a DC, BA. Okay, then how about the galvanometer now to deflect? The deflected go to the right. So this one is the first diagram what they show you. Okay, now until here. Can you see the black color commutator up already? So this one is a when 90 degrees. Okay, now 90 degrees. Okay, you cannot say, okay, now commutator and carbon brush broken, then no current. Actually, memang no current already here. Okay, when starting, we also no current. I don't care you are joy or never joy, also never mind. Okay, now north to south still the same. Okay, now we're going to see this one situation. North go to south. Okay. Now rotation, force here. Okay. Another force go to left, right, left. Yes or no? Okay. Now I want you to check direction. North go to south is constant. Always go to right. But now I want you to see the force. Force one is go left. You want to turn left. Another one you want to turn right. Okay, you tell me this one situation. parallel or perpendicular. Don't talk about current first. Talking about the force and magnetic flux. Now the force, they push the C, go to left. They push the D, go to the right. So that means, can you see the force and also the magnetic field both in parallel direction? If both in parallel direction, actually we cannot create any induced current, because I told already must be perpendicular. Now the situation is AB and CD. AB and CD, the force now is parallel to the magnetic field. That means the flux lah. And do not cut off the magnetic field line. Okay, they do not cut, they just cross over only. They parallel cross over only. They never cross to exactly 90 degrees. They just, you go right, I go left, like this only. So from here, they say that no induced current. This situation when 90 degrees, no induced current. So what happened for the galvanometer? They go back to zero lah. Because no galvanometer, just now you go right, is it? So this one, they go back to zero. Because you know current already. So from here, they say no induced current produced the instant. So the galvanometer will return to the zero mark. Go back to the zero mark. Why like this? Because no induced current. They don't have any induced current to pass through. So they will go back to zero mark. So for this one situation, you need to explain A. A very important. A, B, and CD now the side. Okay, the motion that's exactly parallel with the magnetic field. So that means they're never cutting the flux. If they're never cutting the flux, that means they cannot produce an induced current. No induced current means the galvanometer don't have any current. They turn back to the zero mark. Okay, but one more thing I want to explain for you. Is it the coil keep the direction like this? The coil is never keep the direction like this. They will automatically turn to the 180 because of the, hello, because of the, yes, because of the inertia. You cannot stop immediately one. Okay, the the inertia exactly, they turn back to the 180. So the situation will go to the number 3 again. Okay, just now the first one, you see the black color at the right hand side. The coil black color at the right hand side. When I turn 180, okay, the black color one go to left hand side already. Okay, the black color still DC, we never change. Okay, now the situation, you point again for me, north to south. Okay, now your force is 1 go down, 1 up. So your direction still, okay, I point again, north to south. Okay, I point the easy one, AB, because AB, the force is up. So the current is far away from you. So I show again, now the current is far away from me, and this one go here. Okay, now come out, go here, and go back. Okay, how about galvanometer now again? Before it's 0, now they will deflected, go to the right. Okay, internal, the coil how to move already, the current, induced current how to move. Now it's from A, B, C, D. Just now is D, C, B, A. Galvanometer go right. Now when 180 turns, galvanometer still right, but internal coil direction become A, B, C, D. Okay, but the rotation same direction, always clockwise. Okay, just the internal become A, B, C, D. Okay, now we go to explain. As the coil continue to rotate, current will again be induced in the coil, but its direction is now opposite. So the opposite how? From the A go to B already. Then from the C go to D. However, the direction of the current through the external coil remain the same. External remain the same. So the galvanometer deflected also go to right. So from number 3, I can prove already. This one sure is a DC one, because your external always produce the current is go to right hand side. Okay, internal we never see one. We just want to see is the external important, because your internal the rotation always the same direction. Okay, then when I go to the number 4, again number 4, the black color one go down already. So now the side A, B, C, D parallel again. Then you're talking parallel. Parallel means no cut about the magnetic field. Then no induced current is produced instant. Now the governor return to the 0 mark. The process repeated. Okay, so this one is what I want to explain about DC generator. This one, rotation, this one is the original. Okay, north to south. Okay, we're going to see the part for the AB. AB because it's up, is it? Because this one is up, this one is come down. That's why the rotation is clockwise. So I show the side AB. AB is up, so up. So the current is come to me. Come to me means I draw the arrow lah. Come to me. This one is far away from me. So come to me like this. Go up. Okay. External. Okay, they will deflected go to right hand side. Okay, deflected go to right hand side. Internal DC B A. Okay, this one is a DC generator. Okay, E final. Finish all the 4 steps. We're going to see the last part. Okay, last part is this one. Conclusion from the 4 part. Okay, if we start with 90 degree first, if we start like vertical first, vertical is nothing happen, because this one is don't have any current one. Cannot produce induced current because you are parallel. So from here, when starting, there's a 0. Starting, there's a 0. Okay, so from here, when I turn until 90 degrees, okay, cannot say 90 now flat already, horizontal already. When horizontal, what happened? Okay, now the current flow, DCBA. Okay, deflected, how to go? They go to the right. So this one produce maximum induced current. Okay, when I turn until 90 degrees, go again. Okay, now vertical again. Vertical means no induced current because cannot cut the flux. Galvanometer go back to the 0 mark. So this one don't have any induced current. Okay, when I turn again 90 degrees, okay, now horizontal back. Horizontal back means you cut the flux again, maximum. So from here, you see the galvanometer still deflected, go to the left-hand side. They never change direction, still go to the left. Okay, but you see the current. The current in the coin now is from the A, B, C, D. Just now is DCBA. Okay, rotation how? Same, always in the clockwise. Okay, now maximum again. Okay, when I turn to 360, vertical again, no induced current again, so become 0. So you see the graph. The graph is always above the horizontal line. Means what? This one is a DC induced current. Okay, DC induced current. Okay, after finish, I need to go to the last part. There's a AC generator. Just now is DC, is it? So that's why you see the graph always above. Now I want to show is a AC. Okay, let's see the AC.
Teacher,
Yes.
can I ask question?
Yes, Cup.
Like what causes the coil to turn? Like it keeps turning, but then how?
You turn, you got something to turn. Must
Oh,
you turn yourself if you know how to turn.
because that one generator
Yeah, generator means, okay, example, have you seen the torchlight before? The torchlight old one now using the battery, is it? Or you go to charge the battery lah. Got one more is using your hand go to rotate. Rotate, then just like your bicycle lah, you go to rotate, then after that got light to come out. That means must have the own go to rotate. Or you using something go to turn, then after can process.
Oh,
That
okay.
means just like the turbine. Turbine to generate electricity. Using what to turn? Using the steam. High pressure steam. Water, after that turn, then they produce.
Okay.
Okay?
Okay,
So
thank you,
from
Jer.
here, all is you need to turn yourself. Okay, there was somebody to help lah.
Okay.
Okay, so this one is generator. Okay, the kinetic energy you must produce by yourself. Okay, example for the simple is a dynamo from your bicycle. That one is a simple concept. That means you need to take your bicycle, you must turn faster, is it? The view must be faster, then after that the light become brighter. So that one is you go to generate your kinetic energy faster, then the induced current increase. For turbine generator, we're using the steam. Because you heat the water, then the water becomes steam. Then the steam high pressure, then they're going to turn the turbine. Okay, using the steam very high pressure, the turbine rotate. Rotate inside sure got magnet because you cut the flux. Then finally generate electricity. Okay, so this one is the concept how to produce a generator. Okay, now we need to see is the last part lah. The last part is AC. Okay, remember before that we learned about the 3.2. We got motor, is it? We got DC and AC motor also. Okay, when I want to say about AC, you remember what I need to change or not? Anybody know? For the circuit, what I need to change? Is it I still using commutator?
Slip rings.
Okay, we're using strip rings. Now you can see this diagram, AC. When AC, don't care what is that. When they just say AC, I don't care you generator or motor, must slip rings. Okay, DC, commutator. AC, strip rings. Okay, motor, using battery. Generator, no battery. That's all. Okay, now we're using the AC. Go to explain. Okay, first one, I want you to see very clear is, okay, this one line. Okay, I draw the red color line. Okay, this one. Okay, this one line, they never go, okay, I label this one P ring, this one Q ring. Actually, the red color one, they never attach to the P ring. They just pass over, then they touch to the Q. That means P not related with the red color line. The one red color line just pass over, then go to the Q only. Okay, another one are using the green color. Okay, another one is at here, the P1. This one go. This one is touching about P. So see, every link, they got personal coil wire. The ring Q is a red color coil wire. Ring P is a green color. Then everyone got personal carbon brush. So now I want you to imagine this one is 0 degree. When I turn 180, what you think about that? This one green color will go to this side. Agree or not? Go to the right hand side. The red color will go to the left hand side. Agree or not? Agree or not? Green at the same ring will go to right hand side. Red at the same ring Q, they will go to left hand side. So that means I never share about the ring, you know. The ring and the wire always the same ring and same wire. The wire just left and right, like this only. Okay, so I need to continue to explain already. Okay, now the two ends of the coin are connected to slip rings. That means a pair of the slip rings, which rotate with the coin. Every ring is always in contact with the same carbon brush. That means carbon brush, no sharing. We keep using the personal one. Okay, now we go to step by step to explain for the AC. Okay, first part, north to south. Okay, B is down, the force is down. CD is up. This one is rotation in anti-clockwise. Okay, now we point again our right hand side, north to south. Okay, we point the easy one. Thumb is up. Which part is a up? DC is a up, is it? So we thumb the up. Okay, now you take out your finger, second finger. Second finger is far away from you. Far away from you means D to C. Okay, then this one come down. Okay, now we're going to see the outside. Inside we know already. Now I want to see the outside. Outside is come to here. Okay, then go back the Q, then go in. Okay, now you need to see very clear. Ring P, join with the coin AB. Ring Q, join with the coin line is a DC. Okay, so if the galvanometer show here is a 0, now they need to deflect it to this part. Okay, they need to deflect it to this direction because you turn like this. Okay, now I need to answer. Coin AB, move downwards. Coin AB, move downwards. Coin CD, move upwards. Okay, when the coin rotates, okay, now you continue again. The side across the magnetic field. Then after that, they cut lah. Then the induced current flow in the coil from, okay, now it's D to C. Then B to A. Okay, how I know? Using Fleming right hand. Okay, in the external circuit, how? The current flow from which one ring? From the P ring, go to the Q ring. Okay, for the first diagram, anybody want to ask? I want to prove, later I want to prove how to produce AC. Kaijie, are you here? Kaijie, are you here? Don't know, go away already. Chua Jianing got mic or not?
Got.
Then understand the first diagram?
Understand.
Okay, so I continue. Ji Hui Ni got mic or not?
Hmm?
You just come in.
No.
Then you understand or not?
Mm.
Means what? Yes or no?
Understand.
Understand. So I continue. Okay, first I finish. When there's a horizontal. Okay, now. Okay, we remember first. The direction internal is DCBA. Okay? Induced current. External. External is from the P go to Q. P ring go to Q ring. Okay, now I continue. Okay, when there's a in vertical. Okay, vertical is the same thing. AB and CD now parallel. Okay, the force now is go to left, then one is go to the right. So now it's a parallel already. Parallel means they never cut the magnetic field line. No induced current. Galvanometer, they go back to the 0 mark because of no induced current. So the second one should be the same lah. Okay, don't care you are DC or AC lah. So there's a no induced current. Induced current. Okay, then we go continue horizontal again. Now horizontal, I want you to make sure, just now, okay, the ring join with this one, the short one, okay? That's a P ring. The longest one, they are using blue color, they join with the Q, okay? Like this, Okay, now, when I turn 180, can you see the blue color go to left-hand side already? Hey, hello. Wait, I go to draw properly first. Okay, the Q here, join to this one. Okay, now the P still the same. The coin is the same one. Just they rotate left and right only. Okay, it's the same thing. You see the Q. Q is the side DC, is it? Okay, from here. Q also is a, okay, DC one. still the DC one. They never change anything. Okay, just the ring. Okay, just now is here. Okay, when another side, they become here. Like this only. Okay, so from here we need to check again the induced current. Okay, now this one is go down, this part is go up. So we join again. So this one is A to B, C to D. Okay, so now I write the internal current how to flow, A, B, C to D. Okay, now outside, see very careful outside. From the CD, okay, they never go to P. P just cross over, just cross only. Cross the ring, then come to the Q. Okay, after that, go to the P. Okay, if the zero galvanometer is here, now the diffracted go to the right. Okay, diffracted go to the right. Means now the external current how to flow from the Q go to the P. Okay, from the Q pergi P. So from here we answer the question. Okay, after the vertical position, the current increases until it attains the maximum value. Okay, I told you already, when the keep rotate, you cannot say no current, God, because you are not exactly 90, maybe you're 20. 20 also got current, very small. Until maximum is how many? 90 degrees or exactly perpendicular. So from here, they say the coil CD move downwards. Then the AB go upwards. Direction current how to flow. Now is A to B, then C pergi D. Last one, direction of the current through the external circuit now is from the Q go to P. So I want you to compare the first one, P to Q. Second one, Q to P. So this one, they produce what current? There's an alternating current. The external produce alternating current, but inside the rotation, how? No changes. The rotation must be keep anti-clockwise to change. Okay, so you want to produce the AC, you must using the slip rings. You see the slip ring and the commutator is a different thing. Okay, they got join with the coil, they're using the two ring, they don't want to share. If you share later, you find it your rotation cannot same direction. Your rotation later anti-clockwise, anti-clockwise. That means your motor cannot function like this. Generator also cannot function. You want the generator to function, the turning must be always in same direction. Okay, so we go to the last part. Last part again, the side A, B, and C, D are moving parallel. Okay, to the magnetic field and do not cut off the magnetic field line. No induced current is produced at the instant. Galvanometer go back to the zero mark, then repeat. Okay, so this one is the AC generator. Okay, AC generator we want to see is the external one. Internal we no need to see one. Well, you see your fan keep turning, is it? Inside how to turn we don't know. Important we see the blade how to turn. The blade always turn in same direction. That one is a motor. Okay, 1 until 4. Any question? So I show you the diagram. Same again the diagram, but now it's AC. Okay, it's this part. Okay, same lah. This one is 2 receipt rings. Can you see I talking about this wire lah? The wire longest and the shortest one. The longest one join with this ring. The shortest one join with this ring. Always, never change. When you terbalik, the coin you turn 180, just this one shorter one will go to this side. And the longest one will go to another side. The ring still the same. Okay, this one is the slip rings. Okay, after that, rotate. Then we go and see the final rotation, the graph how to plot. faster. Okay, we see how to plot lah. Okay, this one. Okay, this one is the final for the AC. Okay, when there's in vertical, we're talking about the parallel lah. When parallel, that means don't have any induced current produced for the external. So after that, you find it there's a galvanometer never deflected. So induced current is a 0. Okay, when horizontal, so from here the galvanometer, they show the current, galvanometer turn to left hand side. So this one, they produce a maximum induced current. Okay, when they rotate again, until vertical, okay, now again parallel, no induced current, becomes 0. Okay, now continue to turning for the blade. So you find it, galvanometer go to right hand side. This one is a left, this one is a right. So I know this part is a maximum induced current, but in opposite direction. So you see the graph now go downwards, maximum, and turn back, go to 0. So this one is what current? AC induced current. Okay, they produce the external is an AC induced current. Okay, yeah? So I can conclude is, okay, AC, yeah, slip rings. Okay, generator or motor also same. When I'm talking about AC, must slip rings. Okay, DC, must commutator. Okay, don't care you are motor or don't care you are generator. Still using commutator. Okay, now separate. Okay, now I'm talking about battery. Battery, not motor, not about the AC/DC. Now I say battery. Okay, wait. Battery. Battery, sure, motor. Okay. Galvanometer, sure, generator. Okay, AC, DC also can. Motor never mind one. You want produce AC, you want DC also can one. Okay, if I using battery, sure is a DC law. If I want to using the AC, I'm using the power supply law. Okay, power supply the chain become AC law. Okay, for the generator, galvanometer one only. Okay, you don't have any battery, no need to adjust about the battery, just galvanometer, that's all. Okay, generator also can AC, also can DC. That one is you generate one. Okay, motor, you want using AC current go in also can, DC go in also can. If you're using DC, then you choose here law. If you're using DC, then must using commutator. If you want to using the AC motor, you must choose slip rings. Okay, for the generator, you just put galvanometer. You want to produce a AC galvanometer, then you're using the slip rings. If you want to produce a DC galvanometer, then you're using commutator. That's all. Like this. This one is a fix. This one is a fix. Motor must battery. Generator must be galvanometer. Okay. Hello. Okay, one more easier to remember. Motor. We see motor first. Motor is start with M. M is a man. Man using what hand? Man is a left hand. Motor for man. Left hand rule. Okay, generator start with G. Is it G is what? G is a girl. Girl is right hand one. Girl is always right. So there's a right hand. Right hand means right hand rule. Okay. Motor, man, left hand rule. Girl always right, then right hand. That's a generator. Okay, understand?
Understand?
Okay, so that means my lesson, we go to the last page lah. This one is the last before I close it. So this one explain. Okay, now I want to see the factor to affect the magnitude of the induced current. How to make the induced current become strong? First one must be magnet very good law. Magnetic field become good law. Number two, your number of winding for the armature. Okay, this one is a coin, is it? Actually, the coin is ring by the wire. The wire coil turning for the coin. If I turning more, that means your coil later produce magnetic flux is more. Okay, if I ring the wire less, that means later you cut the flux become less low, like this only. So they say the winding on the armature, number of the winding coil. Okay, presence of the iron core in the armature. If I using the iron core is better. Okay, if we're using the iron core is better. Okay, after that, the speed rotation for the armature, you will turn faster also is a good. Last one, area of the armature. If the area of the armature become bigger, they say it's very good. Why? If the area become bigger, mean this one situation, they produce the flux at the center is more. Further a little bit, then you cut, also will good. So I do, okay, area lah. Maybe I say area, I using the wire become more lah, also can. Okay. So this one is how to make the induced current stronger. Important you think about that. Which one is a straight? We know there's a speed. Speed is the first thing we know how to increase the induced current. Rotate faster, sure faster one. Sure more induced current to come out. Number two, sure is a magnetic field. Yeah, the rest one, you want area bigger, you want coil more, that one is a sub lah. Okay, so this one is how to increase the induced current. Okay, everybody. So our lesson is coming soon off law. You understand or not what I'm talking about? For 2 hours today.
Understand.
Just in only ah.
Half understand.
Or half some more. Xiao Liao, I teaching all. You say you half ah.
Teacher, my understanding not good ma. Later still need to...
Later. You must repeat one. Every time your understanding is repeat. Okay, the others? The others, are you okay? Kan Jiawei today, nothing to say. Oh. Jiawei? Jiawei, are you here? Jiawei disappeared.
Yes, teacher.
Oh, yes. I later got question. You PM me.
Okay.
Okay, so my lesson. So there's until here, low. So the coming soon. I will continue my chapter 5 because my chapter 5 cannot finish already. I still until 5.3 only. Then the coming one, I also will upload lah. Then after that, coming soon is what? 5.4, is it? Coming soon is a 5.4. So the 5.4, I also will upload as a YouTube. So you refer the YouTube. I need to finish the chapter 5. So the chapter 3, you need to complete your tutorial first. I'm teaching already. You complete your tutorial. Then the tutorial lesson, I also will make it as a YouTube. So make sure you go to YouTube, then you check the answer. Okay, so anybody got question? Can ask now. Got or not?
No.
Got or not? No, So after that, you got problem, you PM me. You snap the photo, then you PM me.
Okay.
Okay, Yong Eun, are you okay?
Okay.
Okay, so our lesson is until here only lah. Thank you for your waste the sleeping time to follow my lesson. So from here or finish already, then you go back to sleep already. Okay, bye.